The K-Jetronic fuel injection system provides continuous but varied amounts of fuel to the induction tract of each of the engine cylinders. The quantity of fuel is controlled by the airflow meter, which is placed in the air intake. Because each cylinder receives the precise quantity of fuel for any operating condition, higher engine efficiency is achieved. Prompt response, brisk acceleration, high power output, and low levels of noxious gases are all benefits enjoyed by the owners of vehicles which have K-Jetronic fuel injection. The system was first introduced in the 1970s and has since undergone many changes. During this program, however, we will be describing the operation of the basic system. The tape is divided into sections, each describing a component within the system. Future programs will describe the additional items which have been fitted, along with fault diagnosis and testing procedures. The fuel tank. Vehicles are fitted either with a pressurized fuel tank or a normal vented tank. The pressurized tank uses a special ventilation valve fitted here in the breather system to maintain an air pressure inside the tank of 0.3 bar. The pressure is created by the natural gassing of the fuel. The valve works in the same way as the radiator cap, fitted to a cooling system. Excess pressure is released to atmosphere by an internal valve lifting off its seat against spring pressure. A second valve allows air to be admitted into the tank as the fuel level and temperature falls. The lower half of the ventilation valve may include a gravity valve, which prevents fuel from spilling out of the breather pipe in the event of the vehicle turning over during an accident. This is done by a ball which moves this cone valve onto its seat, so closing the outlet. Because of this gravity valve, it is important that the ventilation valve is always fitted vertically on the vehicle. There are various types of ventilation valves, so always consult the parts microfiche when renewing one. A gauze-type filter and water separator is fitted either in the fuel tank or the external fuel line to the pump. This is additional to the main filter. The electric fuel pump. The fuel is drawn out of the tank by an electric pump. The pump requires at least 11.5 volts to operate efficiently, which it receives from the fuel pump relay. The relay is energized by the ignition system, and for safety reasons, switches the pump off as soon as the engine stops turning. Fitted here to the outlet side of the pump is a replaceable non-return valve, which prevents any fuel from flowing back into the tank. On some models, the pump is installed inside the tank. The 1985 Golf GTI uses two pumps, a small one within the tank and a second larger one outside. The accumulator. When the engine is switched off, the accumulator maintains a residual line pressure in the system. This is known as holding pressure and is essential for hot starting capability. An additional benefit is that the formation of vapor is minimized. When the engine is running, fuel is pumped into the accumulator and passes this baffle. This change of direction helps to absorb some of the noise pulses generated by the pump. Fuel now fills the chamber and forces the diaphragm back against the spring until the stop contacts the casing. The diaphragm remains in this position all the time the engine is running. When the engine is switched off, the spring now pushes the diaphragm back in the opposite direction, maintaining the holding pressure in the fuel lines. Don't forget that fuel is prevented from returning to the tank by the non-return valve in the pump. The fuel filter. The fuel filter cleans the fuel which passes through it from the accumulator. It is either situated in the engine compartment or underneath the vehicle near the accumulator. The filter consists of a fine paper element which removes any dirt before the fuel reaches the main part of the injection system. Some models include a non-return valve in the outlet union, which prevents the fuel from escaping if the fuel lines are damaged. Remember, it is important to check in the maintenance schedule when and if the filter needs replacing. Fuel metering unit. From the filter, fuel flows into the fuel metering unit, which is the heart of the K-Jetronic system. The metering unit contains a number of chambers, which equates with the number of engine cylinders. For ease of explanation, only 2 of these chambers are shown. The chambers are divided in half by a thin steel diaphragm, providing an upper and lower half to each chamber. The lower chambers are interconnected, so fuel can flow into all of them. When the fuel pump is running, fuel is delivered via the accumulator and filter to the metering unit lower chambers, and then, via a return line, back to the tank. This fuel flows continuously whilst the engine is running. Fitted as an integral part in the metering unit is a pressure regulating valve and spring. The regulating valve is fitted with a rubber O-ring to form a good seal. It is held on its seat by the spring, the tension of which is adjustable by steel shims. With the engine switched off, the regulating valve closes, and therefore no fuel can return to the tank via the return line. With the engine running, fuel delivered by the pump builds up a pressure in the fuel lines and lower chambers. Once this pressure rises above that of the spring tension, the regulating valve opens and allows excess fuel to return to the tank. The action of this valve maintains a constant pressure in the system. This pressure is referred to as the system pressure. By adding or removing shims, it is possible to adjust system pressure exactly to manufacturer's specified figures. Situated in the center of the metering unit is a stepped control plunger assembly. The control plunger fits into an open-ended cylinder, which has a number of slots at its upper end, called metering slots, and an equal number of holes at its lower end. The metering slots connect directly to the upper chambers, while the lower holes connect to the lower chambers. The plunger moves up and down in the cylinder very smoothly, both parts having been machined to exact tolerances to ensure a fuel-tight seal. With the plunger down in its rest position, fuel can flow in through the holes and around the stepped section of the plunger, but can't pass into the metering slots. However, if the plunger is raised slightly, then a small section of the metering slots is uncovered by the plunger, allowing fuel to flow from the bottom chambers into the top. These slots are very accurately machined and ensure that an equal amount of fuel is distributed to each chamber. The top chambers in detail. Each top chamber has a small diameter outlet which extends down to just above the steel diaphragm. Fitted around this outlet is a light coil spring which exerts a slight downward pressure on the diaphragm. On the outside of the metering unit, each of these outlets is connected via a pipe to a fuel injector. Hence, the number of chambers corresponds directly to the number of injectors and therefore the number of cylinders, 1 injector per engine cylinder. So let's just recap by looking at the system so far. We will assume that the plunger is in its fully down rest position and the fuel pump is running. Fuel is delivered to the lower chambers by the fuel pump and the system pressure is maintained by the regulating valve. With the plunger at rest, no fuel pressure can get into the upper chambers. The system pressure pushing up on the diaphragm flexes it upwards and closes the outlets. Therefore, no fuel flows out to the injectors. However, if the plunger is raised, the metering slots are uncovered slightly and fuel under system pressure can now flow into the top chambers. This pressure, plus the pressure of the springs, flexes the diaphragm back down, which opens the outlets to the injectors. Fuel now flows out to the injectors. Remember that this action is happening at the same time in all the other chambers, and so unlike many other fuel injection systems, all the injectors spray fuel at the same time, continuously. If the plunger is lifted further, then more of the metering slots are uncovered, allowing a greater quantity of fuel to flow out to the injectors. The movement of this plunger is controlled by an arm which is connected to the airflow meter. airflow meter. The airflow meter, or sensor plate assembly, is situated between the air filter and throttle housing. Any air flowing into the engine has to pass this airflow meter. This consists of a circular plate in an alloy housing. With the engine running, airflow causes the plate to lift, which in turn, by a lever system, lifts the control plunger in the metering unit. The further the throttle is opened, the greater is the airflow into the engine. The greater the airflow, the further the plate lifts the control plunger, which increases the quantity of fuel delivered to the injectors. Together, the airflow meter and metering unit maintain the ratio of air and fuel required for correct combustion. It is essential, then, that there are no air leaks between the airflow meter and throttle housing, as this will affect the air-to-fuel ratio, causing it to be excessively lean. A means of adjusting the mixture is provided by an Allen screw situated in the lever assembly. Turning the screw in a clockwise direction raises the plunger slightly to uncover a little more of the metering slots. Hence, the mixture is richened. Turning the screw in the opposite direction lowers the plunger, and the mixture is leaned. Always remove the Allen key after each adjustment. If the key is left in place, it restricts the movement of the airflow meter arm. Opening the throttle may result in air pressure distorting the arm assembly. Injectors. Several different types of injectors have been used over the years, although their operation remains the same. The injectors continually spray a fine atomized mist of fuel into the inlet manifold behind each inlet valve. These injectors open and spray at a predetermined pressure, which is set by the manufacturer. No adjustment is either possible or necessary. Each injector fits into an insert which is screwed into the cylinder head. The injector is held in place by a rubber O-ring, making removal simply a matter of pulling the injector out complete with the O-ring. The O-ring must be inspected for cuts before refitting, as an air leak here will cause uneven running. If you have any doubts about their condition, fit a new set of O-rings. Enrichment for cold running. A method of enriching the mixture for cold running is provided by varying the fuel pressure on top of the control plunger. This pressure is controlled by a unit called the warm-up valve. A small quantity of fuel is directed from the bottom chambers via a small restrictor to the top of the control plunger. From here, a pipe connects to the warm-up valve, which is situated on the side of the engine, and from there, back to the tank via the return line. The warm-up valve. The warm-up valve consists of a diaphragm, coil spring, bimetallic spring, and an electric heating element. With the engine cold, the bimetallic spring presses down on the coil spring, thus allowing the diaphragm to relax. In this condition, fuel from above the control plunger flows back to the tank unrestricted, which causes a low fuel pressure above the control plunger. This is called control pressure. As the engine throttle is opened, the airflow meter plate lifts, and likewise the control plunger lifts. However, because there is only a low control pressure above the plunger, both the plate and plunger lift more easily and slightly further, therefore increasing the amount of fuel delivered to the injectors. The mixture is therefore enrichened. All the time the engine is running, electrical current supplied by the fuel pump relay causes the warm-up valve heating element to heat up. This warms the bimetallic spring, causing it to slowly bend away from the coil spring. The coil spring can now exert a pressure on the diaphragm, and in turn, this gradually restricts the flow of fuel back to the tank. Control pressure in the line between the warm-up valve and the top of the control plunger rises and forces the plunger slowly down. This gradually leans off the mixture. The time taken for the warm-up valve to heat up is approximately 3 to 4 minutes. With the engine cold, the warm-up valve creates a low control pressure, therefore a rich mixture. With the engine hot, the warm-up valve creates a high control pressure and so a lean, normal running mixture. Remember that the warm-up valve requires electrical current to heat it up, and not just engine temperature alone. Auxiliary air valve. When the engine is cold, it is also necessary to increase the idle speed as well as enriching the mixture. This increase in idle speed is carried out by the auxiliary air valve, which provides an additional air supply around the closed throttle valve. It consists of a rotary valve, bimetallic spring, and an electric heating element. With the engine cold, the rotary valve is open, allowing additional air into the engine. This additional air still has to flow past the air flow meter, which lifts accordingly. With the valve in this position, the engine idle speed is increased. Once the engine is running, electrical current from the fuel pump relay warms the heating element, causing the bimetallic spring to bend and gradually close the rotary valve. The engine idle speed then slowly returns to normal. Normal idle speed adjustment is by means of a small brass screw, which, when turned, increases or decreases the small amount of air bypassing the normally closed throttle. Cold start valve. Good cold starting is achieved by the fitting of a cold start valve. This valve injects additional fuel directly into the inlet manifold when starting at engine temperatures below 35 degrees C. The cold start valve is supplied with fuel at system pressure from the lower chambers of the metering unit. Electrical current supplied from the starter circuit is used to energize and open this valve. The period of time that fuel is injected by the valve is determined by the thermo time switch. The thermo time switch. The thermo time switch is located in the cylinder head and screws directly into the cooling system. This thermo time switch provides an earth connection to the cold start valve, which is dependent on engine temperature and starter cranking time. Internally, the switch consists of a pair of bimetallic contacts and a heating element, which is supplied with current from the starter circuit. When starting at engine temperatures below 35 degrees C, the bimetallic contacts are closed, and therefore the earth connection to the cold start valve is complete. Whilst the starter is in operation, the cold start valve injects additional fuel into the manifold. At the same time, the thermo time switch heating element receives current from the starter circuit, thus causing the bimetallic contacts to open after a short period of time. This breaks the earth connection to the cold start valve and switches it off. The period of time that the valve injects fuel is between 1 and 8 seconds, dependent on engine coolant temperatures and starter operation. When the engine temperature is above 35 degrees C, the bimetallic contacts are held open by coolant temperature, and therefore the cold start valve is switched off. Improvements to the basic system. The transfer valve. One of the initial improvements made to the K-Jetronic injection system was the inclusion of a transfer valve inside the system pressure regulating valve. When the engine is switched off, the transfer valve closes off the return line from the warm-up valve to the tank. This helps the accumulator to maintain holding pressure for a longer period of time, which improves hot starting even further. This valve is described in more detail in the self-study book. Full load enrichment. 5-cylinder engines are fitted with a different type of warm-up valve to provide additional enrichment during load and acceleration conditions. This is achieved by a second diaphragm inside the lower part of the warm-up valve and a vacuum connection to the inlet manifold. With the engine idling, or in the part throttle range, the low inlet manifold pressure keeps this full throttle diaphragm in its upper position to maintain spring pressure on the valve diaphragm. The control pressure is normal. However, when accelerating, the higher inlet manifold pressure pushes the full throttle diaphragm down, which reduces the spring tension slightly. This causes the valve diaphragm to relax and lower the control pressure, thereby enriching the mixture. That completes our look at the K-Jetronic fuel injection system. As we have already mentioned, since its introduction there have been many changes to this basic system. These are all described in detail in the self-study books which accompany this tape. Future programs will explain the diagnosis and testing procedures required to trace and repair faults quickly and efficiently within the K-Jetronic system.